Hello and welcome to this film about reversible reactions. It's the first in a series of films about reversible reactions, but I don't know how many there are at this stage. There's going to be quite a few of them. This one's meant to really just be an introduction to the topic, so it deals with how we represent reversible reactions in chemistry and some of the conventions that we follow when we're talking about them, and we'll also look at what Le Chatelier's principle tells us about a system that is at equilibrium. Okay, so let's start off by looking at a reversible reaction the way it might be shown on the page. Okay, hopefully you've spotted already that it's got an unusual looking arrow in it. Okay, that is to say that it can go in one direction or the other, this reaction. Okay, so that's the thing to look out for. If you see that double-headed arrow, you know you've got a reversible reaction. We're still going to call the things on the left of it the reactants, and we're still going to call the things on the right of it the products. But I suppose what's key about a reversible reaction is that the products could actually turn back into the reactants. So I could equally well write this reversible system as these products as the reactants. Okay, so I could put them on the left of the arrow, and then I'd have N2 and 3H2 over here. Now if I wrote the system this way, then the ammonia would become the reactants, and this would become over here, because it's the right hand side, it would be the product side. Okay, obviously it kind of makes no sense to say that ammonia is either products or reactants. It just depends on how we write the equation. So the thing on the left by convention is referred to as the reactant. Okay, and according to our conventions again, the forward reaction is the one that goes from left to right in the kind of the usual way, and the backward one is the one that goes from right to left. So in this top equation, the backward process refers to ammonia turning into nitrogen and hydrogen, the forward one, nitrogen and hydrogen turning into ammonia. But in this case, because left to right will always be forward and this will always be back, in this case, just the way we've written it, even though it's the same equilibrium system, by convention, when we write it this way, we say that ammonia turning into those things is the forward reaction, and that's the backward reaction. Okay, so forward will always go right, back will always go left, reactants will always be on the left, products will always be on the right, but I guess which process is which, and whether reactants are these things or those things, depends on which way you write the reversible system down. Okay. This slide looks at the characteristics of a system at equilibrium and actually shows you a system that is kind of observing an equilibrium condition. Okay, this isn't a closed system because water can escape from this system and more water can get in. For example, if it rained here, there'd be more water in it. But there is a balance of two processes going on, and if we imagine that nothing could get in and out of here and this was a closed system, then we'd have a forward process which we might call melting of the iceberg. As you know, there's lots of it underwater here, which is why I've drawn this great big blob. Okay, and there might be a reverse process which we would call freezing. Okay, so there's these two processes, the forward and the back is the way I've written them. Okay, and what we're going to look at is what the macroscopic properties of a system at equilibrium are, and what rates have got to do with anything here. Okay, so if we start off by understanding what macroscopic means you can see it with your eyes. Okay, it's observable from a distance, as opposed to microscopic where you have to get really very, very close indeed to see it. Okay, so on a macroscopic level, if this system was at equilibrium, it would seem as though the amount of ice and the amount of water wasn't changing. Okay, the iceberg isn't melting and it's not getting any bigger. Okay, so in other words, the concentrations of ice and water in this system are constant. So on a macroscopic level, the characteristics of an equilibrium system are that the concentrations of reactants and products remain constant. How can they remain constant? Well, if this ice is melting at the same rate that it's freezing, then there won't be any change in the amount of it. So the rates will always be the same at equilibrium. Okay, notice that the concentrations don't have to be the same. Okay, we can have lots of ice or lots of water. As long as they're constant, then the system is at equilibrium. systems are often called dynamic equilibria because they're still moving. So the reason for these concentrations is not, for these concentrations remaining constant is not that these two processes have stopped. It's just that they're happening at the same rate. So characteristics of a system at equilibrium, concentrations of everything remains constant because the rates of the forward and backward reactions are the same. Okay, moving on to Le Chatelier's principle. Le Chatelier's principle was named after a famous French chemist. I'll let you decide which of these two Le Chatelier's it is. Or if you can't guess, then a simple Google search will come up with the answer for you. Le Chatelier's principle refers to a closed system. Now, a closed system is one in which no reactants or products can escape or enter the system. So things can't get in or out. So it's usually in a sealed container. And Le Chatelier's principle says that for any closed system at equilibrium, that system will respond in such a way as to minimize any imposed change. So if you remember, we were just looking at a reversible or an equilibrium system that had ice as the reactant and water as the product. Okay. If we establish a closed system with ice and water, so maybe a sealed glass vessel with some ice in it and some water, if I heated it up, Le Chatelier's principle says that it would try and cool itself down because it's trying to minimize the change. If I pressurized it, increase the pressure, Le Chatelier's principle says it would try and reduce the pressure if possible. Okay? If I added some ice, Le Chatelier's principle says that it would try and remove the ice if it could, okay? Because it's always trying to minimize the change I'm imposing. So in other words, it's almost as if it's stubborn. It's trying to do the opposite of what I'm imposing upon it. Okay, now this is an important principle to understand. It's not an important principle to be able to quote, which is why I haven't put it on this slide. If you're doing Year 11 or Year 12 waste chemistry, it's not an important principle to be able to actually regurgitate in an exam. But the understanding what it means for us is really important, and we'll have a look at that in future films. Okay, so we're just going to finish up by looking at a few key terms that we use to refer to reversible reactions. Here we are, we've got this very famous reversible reaction that's used in the Haber process, which no doubt you'll hear much more about in future. Again, we're looking for this reversible arrow, or the double-headed arrow, to show that the reaction is reversible. And just wanted to illustrate the way that we can kind of describe whether this this system is kind of producing a lot of products or whether it's not producing very many and it's staying at the reactant side. So yield, to begin with. Yield is a term that refers to how much of the product we form when the system reaches equilibrium. Okay, so if it was 100% yield, then I wouldn't have any nitrogen and hydrogen in my equilibrium system. I'd just have ammonia. If it was a 50% yield, then I'd have half products, half reactants. Okay, and another way of describing how much of reactants and products there is in an equilibrium system is to talk about the position of equilibrium. Okay, and the position of equilibrium can be left or right. Okay, so when we often refer to the position of equilibrium shifting according to Le Chatelier's principle. So for example, if I added nitrogen to this system, okay, Le Chatelier's principle says it's going to try and remove nitrogen. How does it remove nitrogen? It has to make ammonia from it. Okay, so the position of equilibrium would shift right according to Le Chatelier's principle if I added some nitrogen. But we're going to look much more in future films at how we can actually make equilibrium systems change. So this really is just an overview for now. Right, that's about it for this film. The next two films concern themselves with the kind of graphs that you see when you're studying equilibrium. So they're the ones to go on to next.